Alright, everyone. Now we got the basic understanding about the dimensionless numbers and the transport analogy. Now I think it's the right time to talk and discuss some question related to transport analogy. I have created a question and that is taken from the book BSL, which is guided by our prof, and we're going to discuss one of its questions. So let's get into it. So the question states, water evaporates from a weighted surface of rectangular shape when air is at 180 and 35 degrees centigrade is blown over the surface at a velocity of 15 meters per second. Heat transfer measurement indicate that for air at 180 and 35 degrees centigrade, the average heat transfer coefficient is given by the following empirical relation. Apply Chilton-Coulomb analogy to estimate the mass transfer coefficient and the rate of evaporation of water from the surface if the area is 1.5 meters square. So the question basic understanding says that there is a weighted surface of area 1.5 meter per square and water evaporates from the weighted surface by flow of velocity which is flowing at 15 meter per second. So we need to use Chilton-Coulomb analogy to find the mass transfer coefficient which is K and rate of evaporation of water which is NAW naught. Additionally, the question also states that average heat transfer coefficient is given by 21 V infinity raised to zero point 0.6, where H average is in watt per meter square Kelvin, and V infinity as in air velocity is in meter per second. More information given in this question was about water at 35 degrees centigrade or 308 Kelvin. At 308 Kelvin, the pressure which is pressure saturation is 0.0562 bar, and the diffusion coefficient of water in air we can also tell it as DAB at 313 Kelvin is 2.88 into 10 raised to minus 5 meter square per second. So according to the question, we need to find at 35 degrees centigrade, which is 35 plus 273, which gives us 308 Kelvin. And the diffusion coefficient is given at 313 Kelvin. So we know the analogy, and here comes our first solution, step 1. Step 1 is to find the DAB at 308 Kelvin, that is at 35 degrees centigrade. From the relation that is DAB is directly proportional to T raised to 3 by 2 and inversely proportional to P, we get the equation that DAB is directly proportional to T raised to 3 by 2. From this, we can find DAB at 308 Kelvin. So DAB at 308 Kelvin is equal to DAB at 313 Kelvin into 308 by 313 raised to 3 by 2. And from this, we get DAB at 308 Kelvin is equal to 2.81 into 10 raised to minus 5 meters square per second. From this, we will move on to step number 2, and we need to apply Chilton-Coulomb analogy. As according to the question, we are already stated that we need to apply Chilton-Coulomb analogy. So moving on with this, from the previous segment, you have already learned that F by 2 is equal to STH into PR raised to 2 by 3, and F by 2 is equal to STM into SC into raised to 2 by 3, where STH is equal to Stanton number of heat transfer and STM is equal to Stanton number of mass transfer. Similarly, PR stands for Prandtl number and SC stands for Schmidt number. We need to find STH and STM as these are the two unknowns given in our question. So, previous segment we have already learned that STH is equal to Nu upon Re by PR, which is Nusselt number upon Reynolds number into Prandtl's number, which can be further simplified as H upon rho Cp BCH, or heat transfer coefficient upon density into specific heat into characteristic velocity. Similarly, STM or Stanton for mass transfer can be written as SH upon Reynolds number into Schmidt. It can be further simplified to Kc upon VCH, where SC or Schmidt number is equal to mu upon DAB. Finally, we will move on to the step number 4, which is substituting the missing term. It is nothing but we need to substitute the terms of Schmidt number, which is SC raised to nu by DAB, STM, or STM and STH. So Schmidt number is equal to nu upon d area. Substituting the value, we get the number 0.586. You will notice there is no unit, as we already learned that this is a dimensionless number. So we aren't going to deal with some units in there. Finally, we need to find Kc, which is mass transfer coefficient. So Kc average is equal to H average upon rho Cp into PR upon Schmidt raised to 2 by 3. This is nothing but we just substituted the values of STM into F by 2, which is F by 2 is equal to STM into Schmidt raised to 2 by 3. From this, and substituting the value of V infinity raised to zero point 0.6, we get the value 0.0105 meter per second. With this, we got the first part of our for our question, that is mass transfer coefficient is equal to 0.105. Now, if we will look back to our question, we have already solved the first part. Now we're going to move on to the next part, which says rate of evaporation of water from the surface. So, finally, concluding that, to find the rate of mass transfer, so the question arises, how we will find the rate of mass transfer? We know that mass flux is equal to rate upon area, which is nothing but mass flux is written as Kc into CaW minus C infinity. On multiplying it with the area, we get the rate of mass transfer, that is A into Kc average into CaW minus C infinity. Now the question comes, how we will find CaW? So going back to our question, we get the idea that P saturation at 308 Kelvin is given as 0.0562 bar. So nothing but we are going to substitute CaW is equal to P saturation upon RT, which is nothing but concentration is nothing but pressure upon RT. So P saturation by RT, on substituting, we get the value 2.19 into 10 raised to minus 3 kilomole per meter cube. Finally, substituting all the values to Na dot, that is rate of mass transfer, we get A into Kc average into CaW minus C infinity, which is nothing but 3.45 into 10 raised to minus 4 kilomole per second. So with this, we solved the two parts of the question, that is estimate the mass transfer coefficient and rate of evaporation of water from the surface. I hope you got the pretty clear idea about how we're going to solve the rest of the question if it includes dimensionless numbers, transport analogy. Now, with this, Radha will teach us more about engineering correlation, and you will get much more idea about the engineering correlations.
So everyone, now we will see what is engineering correlations. Why do we need engineering correlations? So, since most engineering problems do not have theoretical solutions, a large portion of engineering analysis is concerned with experimental information, which is usually expressed in terms of engineering correlations. These correlations, however, are limited to a specific geometry, equipment configuration, bounding conditions, and substance. As a result, the values obtained from correlations are not exact, and it is possible to obtain two different answers from two different correlations for the same problem. Therefore, one should keep in mind that the use of a correlation introduces an error in the order of plus minus 25%. Engineering correlations are given in terms of dimensionless numbers, as we have already given you some brief on dimensionless number. So basically, we will use that dimensionless number in defining the engineering correlations. For example, the correlations used to determine the friction factor, heat transfer coefficient, and mass transfer coefficient are generally expressed in the form of, as given in the PPT, friction factor is equals to function of Reynolds number. Nusselt number is equals to Nusselt number is a function of Reynolds number and Prandtl number, and Sherwood number equals to Sherwood number, function of Reynolds number and Schmidt number. Now moving forward, the reference temperature and concentration. So, the evaluation of the dimensionless number that appear in the correlation requires the physical properties of the fluid to be known or estimated. These properties, such as density, viscosity, depend on temperature, either concentration. Temperature and concentration, on the other hand, vary as a function of position. two commonly used reference temperature and concentration are the bulk temperature and concentration and the film temperature or concentration. So now we will see what is bulk temperature and concentration. So for flow inside pipes, the bulk temperature or concentration at a particular location in the pipe is the average temperature or concentration if the fluid were thoroughly mixed, sometimes called the mixing cup temperature or concentration. The bulk temperature and the bulk concentration are denoted by TB and CB respectively and denoted by this. TB is equals to double integration of VN dA divided by double integration of Vn dA. Vn is the component of velocity in the direction of mean flow. And Cv is the concentration, which is equals to double integration of Vn C dA divided by double integration of Vn dA. This will give you the mixing cup temperature or concentration. Basically, this is the average of the temperature and concentration. Now, there will be film temperature and concentration. So, the film temperature Tf and the film concentration Cf are defined as the arithmetic average of the bulk and the surface values. So Tf is equals to Tb plus Tw by 2 and Cf equals to Cb plus Cw by 2, in which Tb is the temperature. Now we will see the film temperature and concentration. So film temperature, it is denoted by Tf and the film concentration, it is denoted by Cf, are defined as the arithmetic average of the bulk and surface values. Example, Tf is equals to Tb plus Tw by 2, which is temperature of bulk Tb, and Tw is a temperature at the wall. And concentration Cf is denoted as Cb plus Cw by 2, in which Cb is the concentration at the bulk and Cw is the concentration at the wall. So basically, these are the film temperature and concentration and bulk temperature and concentration. This you will use further in the engineering correlations. And
Project has taken us to a comprehensive journey through the fundamental concept that connects momentum, heat, and mass transfer, collectively known as transfer phenomena. We began by building a strong foundation with dimensionless numbers, helping us understand how different physical systems can be compared and analyzed on a common scale. Then we moved into the physical interpretation of transport phenomena or transport mechanism, where we broke down the meaning and significance of fluxes, whether it's flow of momentum, heat, or mass.
the core of our project focused on transport analogies, a powerful concept that allows us to draw meaningful comparisons between different modes of transport. We explored analogies like Reynolds, Prandtl, and Chilton-Coleman, understanding how each often allows us to use known data from one transfer mechanism to estimate behavior in another. These analogies are incredibly useful in real-world engineering design, especially when data is limited or experiments are costly.
To reinforce our understanding, we have also included a dedicated question section towards the end of the project. This will not only test our grasp of the knowledge, but also help you visit the key concept or the key points in a more interactive way.
And finally, for a well-rounded grasp of transport phenomena, we highly encourage you to continue watching the other podcast episodes created by our peers. Each one tackles a unique aspect of transport phenomena, and together they form a complete learning experience. Thank you for watching and keep exploring.
Thank you, everyone.